In this last video, we're going to make sure that we solve um, a true IVP for a system of first order linear differential equations. A couple things I want you guys to realize are noted here. We start by seeing that the solutions to the system above, which is right here what our general system would look like, A being our coefficient matrix. This implies that our solutions will be of the form that you see down here. Okay? Where lambda and nu are eigenvalues and eigenvectors of the matrix. So lambda is the eigenvalue, nu is the eigenvector. Okay, just make sure you guys understand that. And then we will solve primarily 2 by 2 systems where the determinant of the matrix for our solutions is non-zero. Therefore, our solutions form a fundamental set of solutions and are therefore linearly independent as well. So to begin, we'll first analyze that our eigenvalues are real and distinct, and because they form a fundamental set of solutions, they have the following general solution that we will begin to analyze and cover. Okay, so to kick things off, we're going to solve the following IVP, which says we have some vector and its derivative is equal to this coefficient matrix with 1, 2, 3, and 2, and an initial condition as well. Okay, so the very first thing we need to do, since we're solving a system of first order differential equations, is to find the eigenvalues for the matrix. So we say, okay, let's do that. Determinant, first step. So this is the number one step. Determinant of A minus lambda I, okay, is going to equal determinant 1 minus lambda, all right, 2, 3, 2 minus lambda, as before. And what this is going to equal is lambda squared minus 3 lambda, okay, minus 4. And this is going to equal lambda plus 1 times lambda minus 4. All right, so this implies when you set this equal to 0, lambda 1, our first eigenvalue, will be negative 1, and lambda 2, the second eigenvalue, will be set equal to 4. Okay, perfect. So with that said, now we move into our second step, which is to determine the eigenvectors for each of these eigenvalues. Okay, so now that we found eigenvalues, now we need to find eigenvectors. Okay, so second step. So let's go ahead and start with the case where lambda 1 equals negative 1. That's our first case. So the matrix that we obtain is 2, 2, 3, and 3. And of course, you get that by plugging in negative 1 to the matrix up above. This gets multiplied to nu 1, nu 2. Remember, nu is the eigenvector that we're trying to solve. This all gets set equal to the 0 vector. Let me go ahead and make that 0 just a little clearer. Okay, so this implies, again, it's not terribly clear what that says. This implies, there we go, 2 times nu 1, or the first element of the eigenvector, plus 2 times nu 2 is set equal to 0. Okay, and this implies that nu 1 is equal to negative nu 2, just by solving that, correct? So therefore, this implies that our eigenvector, which is nu, okay, is actually equal to negative nu 2, right? Getting it in terms of one of these elements, and nu 2, just as we've done before in the past. All right, so this implies that our first eigenvector, okay, which is designated with this 1 up here, our first eigenvector, is going to be equal to negative 1, 1, right? And nu 2 is equal to 1. All done. So that's our first eigenvector. Now let's do the second eigenvector. So that'll be for the case where lambda 2 equals 4. Okay? So solving this one, we end up with -3, 2, 3, -2, okay, multiplied by nu1, nu2, which equals our 0 vector, as before. And this is going to imply we have -3 nu1 plus 2 nu2 equals 0. Okay, so this implies that nu1 is equal to 2 over 3 nu2, right? Cool. So with that being said, the eigenvector then becomes nu, okay, which is going to be 2/3 nu2 and nu2. So getting the first element in terms of nu2 because we can, and that also makes the most sense. And this implies that our second eigenvector, designated with a 2 here, is going to be equal to 2 and 3. And the reason why we don't have the fraction here is because I'm letting nu2 equal 3. Okay, that's the reason why. It makes things simpler for us as well when we do solutions. So just be sure you take note of that. That's a key thing that we do. So therefore, the general solution, which is really nice, is just a combination of the eigenvectors that we found along with the coefficients for the exponential that we're going to use. So, and the exponentials happen to be our eigenvalues as well. So let me go ahead and just remind you guys, the eigenvalue for the first one was -1, so you guys can see all the connections. And the value for the second one was 4, okay? So therefore, the general solution, and this is what makes linear algebra and differential equations so nice when they work together. The general solution is, based off the formula we showed earlier, it's going to be x of t, which is our general solution, which equals c1 e to the minus t, that's -1t, that's the eigenvalue, our first eigenvalue, times the eigenvector that's associated with it, okay, plus c2 times e to the 4t, that's the second eigenvalue, and then we multiply that to the eigenvector, which is 2 and 3. There you go. Okay. So now all we have to do now is find the constants. And to do this simply, we need to apply the initial conditions. So the initial condition, as soon as I can write it here, was 0, -4. And that's going to equal the x vector of 0. And that will be c1. Get the c there. c1, here's your first eigenvector, plus c2, and our second eigenvector. Okay. With that being said, then we can write this as a system, which becomes -c1 plus 2c2, which equals 0. All right, then we have c1 plus, let me make that plus a little cleaner for you guys. Get my pen back. Plus, okay, and it's going to be 3 c2, which equals 4. All right, and all of this implies, as you'll soon see, is that c1, when you solve this, is -8/5, and c2 is equal to -4/5. Okay, so overall, the solution then becomes x of t then equals negative 8 over 5 e to the negative t, negative 1, 1, okay, minus 4/5, and this will be e to the 4t, and the eigenvector was 2 and 3. And that's how we do it. All done. Now, what is this a solution for, right? That's the question. This is a solution for a system, right? A series of first order linear differential equations that is answering a higher order differential equation. So essentially there was a second order differential equation that we wanted to solve. We converted it into a system or a series of first order linear differential equations, and by applying our general rule of using the eigenvalues and the eigenvectors, we're able to actually create a system or a linear algebraic solution to that higher order differential equation. And you'll see this again next week for complex values, and then we'll do it again for Laplace transforms. Okay? Well, that's it for today, guys. Please take a moment to go over your homework. Try to do the problems. I did a few of them already in this lecture, so feel free to review those and go over them again for your homework. And then try your hand at some of those Laplace transforms that we covered earlier this week. You do that, you'll be in very good shape so that by next Tuesday, we'll cover everything you need to know, both for the final and for your homework. And if you have any questions, please feel free to reach out to me. All right. Thank you, guys. Have a great night.